Let's look a little further at covalent bonds, specifically covalent bonding rules and polyatomic ions. So to begin with, your book produces these HNOC rules, and I wanted to look a little deeper and see where do these come from. So for instance, you've got hydrogen, which has one electron, and we know that because of it's in group 1A, and then carbon is in 4A, 5A, 6A, etc. for oxygen. And so you produce these beautiful Lewis structures. But then how do these Lewis structures immediately tell us how something wants to bind? Well, we have these things called bonding pairs and non-bonding pairs. And so if you notice, we have these non-bonding pairs. Each electron has another one right beside it. It's nice and happy. It has a partner. But then you have these non-bonding pairs that are sad. They really want a partner. But they don't have one, so they're going to try and find one, either through an ionic bond or a covalent bond. The number of bonds that an element can have is going to come directly from the number of bonding pairs that it contains. So if you look at hydrogen, it has one bonding pair, so it's going to form one bond. Carbon has 4 bonding pairs, so it's going to form 4 bonds. Nitrogen has 3 bonding pairs, so it's going to form 3 bonds. And oxygen has 2 bonding pairs, so it's going to form 2 bonds. Now remember, these rules just come directly from those Lewis structures that you've already learned how to draw. So here's some examples from your textbook that show how you use non-bonding pairs to form bonds. So if you look at this first one, oxygen has 2 bonding pairs available to bond with hydrogen's 1 bonding pair. So this pair will attach here, and this pair will attach here, and that's what you see for water here. Each one of these is a shared bond or a line for a bond. Same thing for nitrogen, that's why it has 3 hydrogens attached to it. Carbon, it has 4 of these non-bonding pairs, so 4 hydrogens will attach to it. Alright, so let's look at this. This is a pretty chart that your book published that shows you just kind of in a pictorial form how many bonds are typically formed for each of these elements here. Additionally, we can use non-bonding pairs to form what's called a polyatomic ion. So remember, polyatomic means there's more than 2 atoms, and in this case they're going to form an ion. So oxygen wants to have 2 hydrogens attached to it, but in this case it's going to form hydroxide, and it's only going to have 1 electron coming from the proton, which means it steals an electron from somebody else. And so in that case now, it has all 8 electrons in its octet, and it has a satisfied, stable configuration. And so what that means is we need to have a balance of mass. Remember back from the very beginning where we talked about law of conservation of mass? There's also a similar rule called law of conservation of charge. So what those will tell us is that we need to have the same number of oxygens on both sides of the arrow, the same number of hydrogens on both sides of the arrow, and the same number of charge on both sides of the arrow. So notice that negative comes from the number of electrons that were added to it. Your book tells you a whole bunch of common polyatomic ions that you can look at for reference. It also draws some of the more complicated figures here for you to look at. But use this as a reference sheet. For the sulfate ion, it's going to be SO4 2-, and so on and so forth. But the important thing with these polyatomic ions, you need to be able to see CO3 within a chemical formula and know that it correlates with carbonate. Because if you don't, you're never going to be able to draw the structure. And so you need to be familiar enough with this list that it's not going to slow you down when you're solving problems, because we're about ready to form compounds using these ions, and if you don't realize that they're a polyatomic ion, you might get really confused. So let's try it. Let's try to form some compounds with these polyatomic ions. You treat them the exact same way as you would have an ion. In fact, what I recommend doing is I recommend putting parentheses around the covalent unit, which in this case is NH4, with parentheses and the charge on the outside. Because then when you're bonding it with a different ion, it's the same process as before, where you would just cross the charges. This 2 would become the subscript outside of the parentheses. That does matter, and this one is on the bottom as a subscript for sulfur. Okay, so for instance, whenever I'm doing these type of chemical equations, if I've got like magnesium bonding with nitrate, I want to be able to write it like this with the parentheses, because now I can cross the charges and put those charges right outside it, and I'm not going to get confused. I'm just going to leave it like that, because if it doesn't matter what's inside the parentheses, all that matters in writing the chemical formula is that you can cross the charge appropriately. Now when you name it, you just simply name your first element, and then your second group, but in this case you use the polyatomic name, nitrate. This one, cross the 3, cross the 2 to become this formula, which is aluminum, and then this group is called sulfate. So you make it sulfate. This ATE or the ITE, anytime you see those in a chemical name, those should immediately tell you that there's a polyatomic ion present. Here's another example, this time with iron 3. So it told you Fe3 plus was the ion, and oxalate. So this is going back the other direction. Then you would look up oxalate and see that it's C2O7 with the whole group containing a 2 negative charge. So C2 and O7, those are all chemically covalently bound inside of it, but the whole group has a charge, which means it can act as an ion. Now you cross those ionic charges, put the 2 down here, put the 3 outside the parentheses, and you've figured out what the formula is. So let's do a whole bunch of practice. So first, what I want you to do is for these first 5 in particular, but then also for these, I want you to figure out what ions are produced by them. Okay, so for these, sodium and carbonate. Sodium, we know it's Na. What's the charge? +1. Carbonate, go look it up in your list. You can see it's CO3, 2 minus. Calcium permanganate. Calcium, go look it up on your periodic table. It's got a +2 charge. Permanganate, MO4 with a -1 charge. Do that for each of these. Okay, then for these bottom ones, you just have to name them. Magnesium's the first element, hydroxide's the name of the group, magnesium hydroxide. You don't have to even figure out what the charges are when you go this order. Okay, when you go the other direction you do, but going this direction you just simply name it. Aluminum and then chromate. Potassium, phosphate, that kind of thing. So now we are done with 6, 7, and 8, but we still need to figure out what's the formula for 1 through 5. So what's the chemical formula for these 5? Alright, all we gotta do is cross those charges. So the sodium has a +1, carbonate has a -2, cross them, and it becomes Na2CO3. And keep doing that for all of them. Test it, see how you did, come see me if you have any questions. Now go read section 4.10.